Welcome to Civil Engineering Edge, your trusted destination for mastering structural engineering. In today's video, we're diving deep into one of the most critical components of any structure, axially loaded columns, as defined by the IS 456-2000 code. Whether you're a civil engineering student, a site engineer, or simply curious about construction design standards, this tutorial will give you a crystal clear understanding. We'll cover the basics of plain concrete and reinforced concrete columns, the minimum and maximum steel percentages, bar diameters, and bar count as per IS code. Let's build knowledge strong and smart. What is axially loaded column? An axially loaded column is a vertical structural member designed to support compressive loads applied directly along its longitudinal axis. In simpler terms, it's a column that takes load in a straight line through its center. According to IS 456-2000, an axially loaded column must be vertically aligned, and the load must be applied without eccentricity, meaning no bending or lateral displacement is involved. These columns play a vital role in transferring loads from slabs, beams, and other structural elements down to the foundation. Axial columns are commonly used in multi-story buildings, industrial sheds, and bridges where vertical load transfer is crucial. Axial load carrying capacity is determined by the cross-sectional area of the column and the type of material used, either plain concrete or reinforced concrete RC. The IS code considers a column short when its effective length is less than 12 times the least lateral dimension and assumes failure occurs due to crushing, not buckling. According to IS 456, any vertical member carrying a compressive force greater than 3 times its least lateral dimension is classified as a column. Understanding axial columns is crucial because design errors can lead to instability or collapse. Hence, IS code guidelines are strictly followed to ensure durability, strength, and safety in real-world applications. Plain concrete columns. Plain concrete columns, as the name suggests, are made of concrete without any steel reinforcement. These columns are suitable only for small, lightly loaded structures or in cases where architectural elements don't carry heavy loads. They rely entirely on the compressive strength of concrete, which limits their use since concrete is weak in tension. According to IS 456-2000, plain concrete columns must meet certain size and load criteria. Since they lack reinforcement, they cannot resist bending, shear, or tensile forces. As a result, they are used mainly for non-structural elements like boundary walls or ornamental pillars. Due to their brittleness and limited load carrying capacity, their application is rare in modern structural design. They serve better in low-rise buildings and places where aesthetics or tradition demand them, but structural load is minimal. Reinforced concrete RC columns. RC columns, or reinforced concrete columns, are structural elements made from concrete reinforced with steel bars, rebars. These columns can resist compression, bending, and shear forces, making them suitable for all types of buildings from residential to skyscrapers. According to IS 456-2000, the reinforcement not only enhances the load carrying capacity, but also addresses concrete's natural weakness in tension. The steel bars are placed in a specific configuration, either as longitudinal bars or lateral ties, spirals depending on whether the column is tied or spiral type. RC columns are classified into short and long columns depending on their slenderness ratio. Design is based on axial load, moment, and interaction curves. They are the backbone of modern reinforced structures, ensuring both strength and ductility. Their versatility and durability make them indispensable in contemporary construction. Minimum and maximum percentage of steel. The percentage of steel reinforcement in an RC column is critical for ensuring structural safety and performance. As per IS 456-2000, the minimum longitudinal steel should be 0.8% of the gross cross-sectional area of the column. This ensures basic tensile resistance and crack control. On the other hand, the maximum percentage of longitudinal steel is 6%, but in practical design, it is often limited to 4% due to placement and compaction difficulties. Exceeding 6% can lead to congestion of bars, making proper concrete flow and vibration difficult during casting. The IS code mandates that minimum for bars must be used in rectangular columns and 6 bars in circular columns. Also, spacing between bars should not exceed 300 millimeters. These percentages strike a balance between economy and performance. Too little steel makes the column vulnerable under load. Too much steel affects constructability and increases cost unnecessarily. Understanding and following these limits ensures the column performs well under both axial and eccentric loading while complying with Indian standard practices. Minimum diameter of bars, according to is 456 to 2000. The minimum diameter of longitudinal reinforcement bars used in RC columns is 12 millimeters. This requirement ensures sufficient tensile strength, ductility, and stability during construction and in service conditions. Using bars smaller than 12 millimeters can lead to inadequate resistance to compressive and tensile stresses, especially in high-rise buildings or seismic zones. This rule applies to both main bars and additional longitudinal reinforcement. Adhering to this specification helps in achieving durability, fire resistance, and long-term performance of the column structure. It also simplifies site handling and concrete pouring operations. Minimum number of bars. The IS 456 to 2000 code specifies the minimum number of longitudinal bars to maintain structural integrity and distribute load evenly. For rectangular or square columns, a minimum of 4 bars must be used. For circular columns, a minimum of 6 bars is mandatory. This ensures proper load transfer, symmetrical reinforcement, and allows lateral ties or spirals to confine the core concrete effectively. Fewer bars may lead to buckling, insufficient ductility, or non-uniform stress distribution, which compromises column performance. Maintaining the minimum number of bars also helps in better crack control and enhances column durability under load variations. And that wraps up our detailed guide on axially loaded columns and IS code specifications. We've learned the difference between plain and RC columns, how to calculate steel requirements, and why bar sizes and counts matter. This knowledge is not just for passing exams, it's essential for safe and practical structural design. If you found this video helpful, make sure to like, share, and subscribe to Civil Engineering Edge for more in-depth tutorials and site-level insights. Got questions or topics you want us to cover next? Drop them in the comments below. Until next time, build smart, build strong.